Hi students, welcome to the big chapter on circles. In order to be thorough with the concept of this chapter, you need to be thorough with the principles, concepts and theorems related to circles. Especially, you must know what is a minor segment, what is a major segment, what is a minor sector, what is a major sector, and what is a chord, what is a secant, and what is a tangent, and properties relating to tangents, properties relating to chords, properties relating to angles on the same segment. All these are detailed in the slides to be followed. Please watch them. Now coming to slide 1, you see in figure 1 the circle has two line segments, one AB and the next line segment is PQ. PQ is a tangent to this circle and it touches the circle at one point R. The segment AB is called the secant of the circle. It passes through the circumference at 2 points. In figure 2, there are several secants and two tangents to circle. There can be several secants to a circle such as P1, Q1, P2, Q2, P3, Q3, P4, Q4, P5, Q5. But there are only two tangents parallel to each other and touching one point of the circle on the left and one point on the right. In figure 3, no tangent can be drawn through a point inside the circle. So a tangent is a line segment touching the circle at only one point. Now in the next slide, circles are said to be equal and congruent if they have equal radii. Two or more circles are said to be concentric if they have the same center but with different radius. OP, OQ, OR are radius of the circle. In this figure, OR is greater than OQ, OQ is greater than OP. Now coming to areas related to circle. Below are two circles with O as its center. AB is a chord of the circle in figure 2. A chord divides the circle into minor segment and major segment. A sector is a region enclosed by two radius arms of the circle with an arc between them. See picture 1. OAB is a minor sector, OAQB is a major sector. Likewise in picture 2, AOB is minor segment, AQB is major segment. In the next slide, a chord is a line segment within the circle whose endpoints lie on the circumference of the circle. The longest chord passing through the center of the circle is the diameter. Here in this figure, OAPB is minor sector, APB is minor segment. Area of sector OAPB is equal to pi r squared into theta the angle by 360 degrees. Area of major sector is equal to OAQB, that is equal to pi r squared minus area of minor sector where r is the radius of the circle. Area of segment APB is equal to area of minor sector OAPB minus area of triangle OAB, and that is half r squared sine theta where r is equal to radius. Area of major segment is equal to pi r squared minus area of minor segment. Arc AB length is equal to 2 pi r into theta angle by 360. The next slide relates to areas relating to circles. Just as in the Cartesian plane in coordinate geometry, the circle 2 has 4 quadrants. Quadrant 1, Quadrant 2, Quadrant 3, Quadrant 4. Area of circle being pi r squared. Pi is either 22 by 7 or 3.14. OA is equal to OB is equal to OC is equal to OD is equal to the radius of the circle. Therefore, area of quadrant circle is 1 by 4 into pi r squared. Area of semicircle is half into pi r squared. Area of 3/4 of a circle is 3 by 4 multiplied by pi r squared. The length of an arc is measured by 2 pi r into 90 degrees by 360. Theta angle is the angle that encloses AD, DC, CB and BA. Here all are 90 degrees. Therefore, 2 pi r into 90 by 360 is the length of arc AD, arc DC, arc CB and arc BA. The next slide, you will see angles in the same segment of a circle are equal. On the left, you see minor segment on which two rays AC and BC meet at an angle theta 1. Also on the same minor segment, two rays AD and BD meet the circumference of the circle at point D, framing an angle of theta 2. Both these angles theta 1 and theta 2 are equal. Therefore, angles in the same major segment are equal. That is, ACB is equal to theta 1 and angle ADB is equal to theta 2. The major segment is above the minor segment. So, angles in any segment, minor or major, are equal. And on the right side, angles in the same minor segment are equal. The minor segment is PQ. So, below PQ, ray PS and SQ meet the circumference of a circle frames an angle theta 3. And rays PR and QR meet the circumference of the circle framing an angle theta 4. Now, angle PSQ is equal to theta 3 is equal to PRQ is equal to theta 4. Therefore, angles on the same segment, whether it is a minor segment or major segment, both are equal. In the next slide, PQR is an arc, major arc. Reflex POR is equal to 290 degree, that is theta 1. PSR is equal to 145 degree, theta 1 by 2. PSR angle formed by major arc PQR. Angle formed by the major arc PQR at the center is 290 degree, which is double than the angle formed by the arc on the circumference of the circle, that is PSR is equal to 145 degree. Angle subtended by the arc AB at the center of the circle is always double than the angle framed by it on the circumference of the circle. Here, angle AOB is equal to theta, angle AOB is equal to 2 angle APB is equal to 2 angle AQB, or angle APB is equal to angle theta by 2. The next slide, we see a theorem from the picture on the left hand side. Equal chords are equidistant from the center of the circle. AB and CD are chords of equal length. The shortest distance from the center of a circle to a chord is its perpendicular, drawn through the center of the circle. Here OM is equal to ON and AB is equal to CD, which means that equal chords are equidistant from the center of the circle. On the right side, arc APB is a part of the circumference of the circle. APB is a minor arc. AQB is the major arc of the circle. Next slide has two theorems. AB is a chord, OP is radius. OP is perpendicular to AB. OP bisects line segment AB into equal parts such that AM is equal to MB. On the right side, AB is the larger chord inside the circle. PQ is the smaller chord inside the circle. Greater the size of the chord, smaller is its distance from its center. OT greater than OS, OS perpendicular to AB, OT perpendicular to PQ. In the next slide, we see two theorems. On the left side, theorem 1, equal chords of a circle subtend equal angles at the center. AB and CD are equal chords. O is the center of the circle. AB is equal to CD, that is equal chords. OA is equal to OB is equal to OC is equal to OD, radius of the circle. All sides being equal, triangle AOB congruent to triangle COB by SSS congruency. Angle AOB thus is equal to angle COD by CPCT, corresponding parts of congruent triangles. The converse of theorem is that if two chords subtend equal angles at the center, then the chords must be of equal length. On the right side, you have another picture, another theorem. OL is a perpendicular drawn to the chord AB from the center of the circle. OA and OB being the radius, OL is perpendicular to AB. OL is a common side. Triangle AOL congruent to triangle BOL by RHS congruency. Therefore, AL is equal to BL by CPCT. That means the perpendicular drawn from the center of a circle to the chord bisects the chord. The converse theorem is that if the line segment drawn from the center of a circle to a chord bisects the chord, then the line segment is perpendicular to the chord. There can be only two tangents to a circle through a point P lying outside the circle. Tangent 1 must be equal to tangent 2. Tangents are equal in length. Let us prove this in the next slide. Now in this slide, tangents drawn from an external point to a circle are equal in length. The external point is A, AV is tangent 1, AC is tangent 2, O is the center of the circle. OB and OA are radius, and OB is perpendicular to T1, radius OC is perpendicular to T2. OB is equal to OC radius, both radius are perpendicular to the tangent. Join OA by construction. Now, OBA and OCA are right triangles, and by Pythagoras theorem, OB squared plus AB squared is equal to OA squared hypotenuse by equation 1. Also, OA squared plus AC squared is equal to OA squared by equation 2. From equation 1 and equation 2, we get OB squared plus AB squared is equal to OA squared plus AC squared. OA squared plus AB squared is equal to OA squared plus AC squared. Now, AB squared is equal to AC squared. Since OA squared is common on both sides, OB being equal to OA, take the square root on both sides, we get AB is equal to AC. Therefore, tangent 1 is equal to tangent 2. Therefore, tangent drawn from an external point to a circle are equal in length. Next slide talks about only one circle can pass through three non-collinear points. On the left side figure you see P, Q and R are non-collinear points not in the same line segment. There could be one and only circle as you see passing through three non-collinear points. On the right side, equal chords in the circle are equidistant from its center. AB and CD are equal chords. OL and OM perpendiculars from the center of the circle bisects AB and CD respectively. Therefore, AB is equal to CD, half AB is equal to half CD, AL is equal to CM, join OA and OC by construction. OA is equal to OC being radius. Angle OLA is equal to angle OMC is equal to 90 degree. Therefore, triangle OAL congruent to triangle OCM. Therefore, OL is equal to OM by CPCT. Therefore, equal chords in the circle are equidistant from its center, that is OL is equal to OM. Now let us deal with inscribed polygons and circumscribed circle. On the left side, the circle is a circumscribed circle because the polygon is inside the circle. On the right side also you see a circumscribed circle because a rectangle is within the circle. The above polygons, triangle and rectangle, are called inscribed polygons. These two polygons are inside the circle. A circle that passes through all vertices of a polygon is called a circumscribed circle. Inscribed polygons are enclosed by a circle with its vertices lying on the circumference of the circle. The polygons here lie completely inside the circle. In the next slide, you see inscribed circle and circumscribed polygon. A circle that touches all sides of a polygon, here in the figure, a triangle, is called the inscribed circle. The triangle here is a circumscribed polygon. The inscribed circle is enclosed by a polygon. Its circumference touches the sides of a polygon at certain points. Here, circle lies inside the polygon, so this circle is called inscribed circle and the polygon is circumscribed polygon. Now let us summarize the basic concepts of circles. 1. Equal chords of a circle subtend equal angles at the center. 2. If the angles subtended by the chords at the center of a circle are equal, then the chords are of equal length. 3. The perpendicular drawn from the center of a circle to the chord bisects the chord. 4. A chord is a line segment within the circle connecting two opposite points on the circumference of the circle. 5. If the radius of a circle bisects chord anywhere in the circle, it is perpendicular to the chord. 6. Equal chords of a circle are equidistant from the center. 7. Chords equidistant from the center of a circle are equal in length. 8. The angles subtended by an arc at the center of a circle are double than the angle subtended by it on any remaining part of the circle. 9. Angles in the same segment of a circle are equal. 10. The angles in a semicircle is a right angle. It means that the angles formed by the diameter of the largest chord on the circumference of a circle is always a right angle, 90 degrees. 11. When two chords intersect within a circle, the product of the segments of one chord equals the product of the segments of the other chord. Two distinct line segments are formed at the point of intersection of a chord. 12. The sum of opposite angles in a cyclic quadrilateral are 180 degrees. 13. When any 2 points on a circle are always concyclic, 3 non-collinear points always define a unique circle. The angle subtended by a common chord on several points lying on the circumference of a circle makes it concyclic. 14. Two distinct circles can intersect at 2 points only, but the intersecting points are non-collinear. 3 or more points on a circle only makes it a unique circle. Two circles intersecting at 2 points A and B has a common chord. The centers of two intersecting circles lie on the perpendicular bisector of AB. It means that the centers of two circles and the points A and B do not lie on the same line segment, so points A and B, the common chord, are non-collinear vis-a-vis the centers of the circle. 16. The tangent of a circle is perpendicular to the radius at any point of its contact. 17. The lengths of two tangents drawn from an external point to a circle are equal. 18. In the picture below, given in the slide, the tangents drawn to a circle from an external point subtend equal angles at the center. Angle POA is equal to angle POB. Also, they are equally inclined to the line joining the center to the point P, external point. That is, OPA is equal to OPB. Now I am pausing for a minute for you to note down these common points. Thank you.